Let's start today's discussion. So, let's see how much justice we can do to these very important topics in the field of optimization, that is, evolutionary strategy and particle swarming optimization. So, yeah, let's start with evolutionary strategy. So, we'll quickly go to the programming aspect as soon as we finish this. A little bit of theory. Okay, so evolutionary strategy. So, sir also has discussed this in the class, and let me just now, yeah. So, what basically is the difference between these technique and the genetic algorithm? What major difference did you see, Mr. Manohar, between this particular strategy and the genetic algorithm?
Yes, sir. May I get
Oh
the
yes,
question?
yes. So the question was, see, we followed some steps for evolutionary strategy. We followed some steps for genetic algorithm. So from the video, what is the difference that pops out between the evolutionary strategy and the genetic algorithm? Okay, so maybe you are sleeping a little bit, but
Actually, I
the
forgot. But
yeah, no problem. So the main difference is there is no crossover.
okay, directly selection and mutation is there.
Yeah.
Crossover step is not present in ES.
Yes, so in evolutionary strategy, crossover is not there. So that is the major difference between the this and genetic algorithm. Okay, so what are the steps? Let's see the steps. So first, we initialize a population. Step two, and after initializing the population, in the step two itself, what we do, we make what do you say, new offspring with mutation. So let's say if this was the X, some set of n number of solutions for this given objective function or problem, then the new offspring was given by y is equal to x plus n0 sigma. Is that correct, Mr. Manohar?
Yes, sir.
Yeah. So if you can recall, so this was normal distribution, normally distributed random variable with mean of 0 and the standard deviation of sigma, which was the main parameter that actually decided how good or bad this evolutionary strategy is. Okay, so this is our offspring. Then what we did, we combined this x and y into a one single population. So initially, let's say our initial solution had n number of solutions. Then we did mutation, and then again we got n number of solutions. We then concatenated these two matrices. Concatenation means if let's say we have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 by 3 matrix, and then again we have 1, 2, 3, 4, 5, 6, 7, 8, 9, this matrix, then concatenation of this thing will just give us 1, 2, 3. So one on top of the other. So we just concatenated these two solution groups to make a new solution. Is that clear?
Yes, sir. Means we will get 6 by 3 matrix.
Yes. So we get a, in this particular example, we get a 6 by 3, 6 by 3 matrix. Now after this, we perform the selection operation. And since initially we had n number of initial population, So after performing this selection operation, we have to, in the end, get n number of final selections also. That will be the new generation, the actual new generation. And then we go on and check the termination criteria, that is whether the solution has improved or not, or whether we have reached the maximum number of allowed iterations. So we check this criteria, and if it is satisfied, the criteria has met, then we go on to give the solution. It may be correct or incorrect based on the criteria, and or if it is not, then we again go to this step 2, that is do the mutation on this new generation, create another new generation, and then combine and do the selection operation, and then just repeat it till we converge. Okay, so is there any doubt? So this theory seems very simple. So this selection operation we can do by a lot of methods, maybe tournaments method, or just simple selection of the best alternate best generation population. So a lot of the things that was discussed in genetic algorithm, that same thing can be applied here also. So Mr. Manohar, if you have any doubt in this particular theory, then you can ask. Otherwise, we will shift move to the programming of evolutionary strategy.
Okay, sir. No doubt.
No doubt.
We
Okay.
can continue.
Okay. So let's go to the programming part. So this is visible my screen.
Yes, sir.
Okay. Okay. So we'll see the problem, same problem that Sir showed, but I will follow a little different approach than him. Okay. So let's see. We'll code together, and we'll see if there is some problem like last time we identified. So it will help us both. Okay. So we don't need to import any package because this is a quite simple approach, and we can do it just by coding. So we are not going to import any package. Let's define the function. So our function is function with two variables, x1 and x2, and inside these curly braces we are going to write what our function is going to do. So it is x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7. Yeah, minus 7. So this is the function that was shown by Sir in the class, and we also use the same function. Okay, so now I have a question, Mr. Manohar. Do you remember the code or the way we generated no, array of variables between minus 5 to 5 by the difference of, let's say, zero point 0.1? Do you remember how to do
We,
that?
we put x1 is equal to x2 is equal to c minus 5 comma 5 and by point 1.
Okay, so a little bit correction is required. So we need actually sequence.
Oh, yes, yes.
Yeah. So C is also correct, but what C will do is it will just give us the sorry, give us whatever these things you put inside. It will convert them into a array. But if you want, let's say you want 4 to 5 uh, with a difference of zero point 0.1, then or something else, then you need a sequence. Okay. So we use this to create an x1 and x2 variable with from minus 5 to 5 with a difference of delta of zero point 0.1. And how do we calculate the value, Mr. Manohar? We want a grid. So if you remember, I told last time, if we need a grid, something, so we use outer. We use outer x1, x2, the variables, and f, function that we give. So it is going to make a grid of x1 and x2, and calculate the value of function at all the points. And then let's see what we have obtained. So we'll plot the contour. So x1, x2, and f value. Then there are two things we can use. So let's say if I want the specific contours that I to plot here, then I will give levels is equal to, again I want to put array here, so I will use C, and let's say I want 100 and 50 and 10 and 1, these many contours I want, and then I will give them some color. Let's say I give it. So this particular code is just going to plot my function in a contour form for these many levels. Okay, so this is the contour I'm getting. So are you able to see this, Mr. Manohar? Oh,
Yes, sir.
okay. So let's say just again let's say I want lot of contours, and I want the contours to start from 1, and I want them to be till 100 and with a difference of 10. So like by the gap of 10. So what do you think I should do? I will need to change the something here only, right?
That levels will be changed.
Yes. And how I should change these things? So I want from 1 to 100 with a difference of 10. How should I get this? So same
Can we
thing.
use the same
Yes.
thing?
Ye-
Minus one to 100 and by instruction for difference.
Yes. So yeah, so the reason why I was telling this is because we can use these methods inside functions also. So let's see if this works or not. As you can see, it is working nicely. Okay? So we
Yes, sir.
have the, yeah. Okay. So now let's see how to solve. So if you remember, we had in the evolutionary strategy, there was one variable which decided whether the solution is good or not. So that is sigma. So let's assign sigma some value. For now, let's just assign one, and we'll see how what happens if we change the value of sigma. And then maximum number of generations or max gen. Let's name them max gen. Let's say we are only going to do for 100 generations. And how many variables do we have in this particular function? We have two variables. Number of variables. Let's name them. Give them value 2. And as always, in any of these meta-heuristic optimization or even conventional optimization techniques, we needed to have initial solution. So let's give initial solution. So what we will do, we will for now what we will do is we will see how this particular optimization technique works by using only one set of solution, like one value of x1 and one value of x2, and after that we are going to just modify this particular expression to to have, let's say, n number of initial guesses and n number of solutions in one generation. For now, let's have only one solution in one generation. So let's say I have initial solution x naught, where the x1 value is 0 and x2 value is 0. So initial solution. Okay. And yeah, let's plot this. We have x naught 1, x naught 2, and so sir has shown this thing that 16 will give a little bigger, PCH 16 is going to give a little bigger filled circle. So let's use that, and let's give the color as blue. Okay, so we have done this. Now let's start to do our optimization. So I will follow a little different approach than what sir had shown in class. So feel free to use when you are doing what sir is doing, or you can also use my approach. Both are going to give similar results. Okay, so what I want to do is I want to run some operation till my generation has reached the maximum allowed generations. So what I will do, I will initialize a variable name generation. I will give it value 1, and I am going to give a while loop which is going to check whether my generation is less than maximum allowed generations or not, and based on that it is going to let me do some operation here. So let's say some operation I want to do. So it is going to check this, then it will let me do the operation. After it, I have done this operation, I will increment my generation variable by 1. Then again it is going to check whether it is less than the maximum generation. Then I will again do the operation. So it's kind of a loop. We are inside a loop. Okay. So is that clear?
Yes, sir.
Okay. So Mr. Manohar, just for curiosity and to save time, so you understand how loops work, and we can move a little bit fast, or do you want me to go with the same speed?
This speed is okay, sir.
Okay. Okay. Thank you. Okay. So let's calculate the value of function at the given solution, whatever inside this loop. Let's calculate that. So let's say we allow f naught, that is the initial population function value. It will go inside f, x naught 1 and x naught 2. So we initialized our population here, and we have calculated the value of the function for this particular value, and we stored it in a variable called f naught. Now that we have stored, let's now introduce. So let me name this as calculate the fitness. Let's call it fitness of initial solution. Then we are going to do mutation to this particular. Now we are going to do the mutation to this particular initial solution, and we are going to check the fitness of the mutated solution. So to do the mutation, if you remember, we had a normally distributed random variable. So how do we get normally distributed random variable? So if I just can just go back to the, let's see. Yeah, so we had this here, normally distributed random variable. So let's see if we can generate. So in R there is a very nice small command to generate normally distributed random variable. That is R norm, R norm. Then you give the number of variables that you want to generate. Let's say I want to generate 5 variables with a mean of let's say 1 and standard deviation of 1. So if I give this, it is going to give me 5 variables that fall on a normally distributed random variable, means a distribution which is normal, or Gaussian Gauss distribution with a mean of 1 and standard deviation of 1. But in our case, so what we had was our norm. We want, how many variables do we have? We have 2 variables. So let's generate two, 2 variables, and the mean was 0, and the standard deviation was sigma. So let's copy this variable here and give this here. So what we have done is we have generated two. Okay, so this is not done. Maybe I will just select this and run this, and yeah. So what it will give us? It will give us 2 variables, which will have mean 0 and sigma that we have specified here. So let's store these variables inside a variable called randomness. Now what we want to do, we want to, so this is not yet the final or the mutated offspring, because we have to add this to our initial solution. So we will create x naught as shown in the expression, x naught plus, so y naught, y is equal to x naught plus randomness. This is going to be similar to what we have written here, y is equal to x naught plus n 0 comma sigma. Okay, so now we have the mutated, you know, generation mutation we have performed. Now let's calculate the fitness of this mutated generation. For that, again, we are going to use the function f, and we are going to put y of 1 and y of mutated generation. Okay. Now what we wanted to do, or what was told in this particular evolutionary strategy algorithm, was if your new mutated generation is better than your particular original or initial population, then you are going to update it. And yeah, so I the problem was of minimization, so let me just mention that here. Minimization problem. So in case of minimization problem, when do we say my new solution is better than my old solution? We say by if my f1 is less than f0. If that is the case, then I will say yes, my my new population is better than my old population. If that is true, I am going to update my x naught to y. So my x naught is changed. Otherwise, I will not update my x naught. My x naught will be whatever I chose initially. So we have done this. Now let's what should we do is we should let's try to see if we can how this solution moves towards one of these points. So for that we'll need points, and we'll plot x naught 1 on x, x naught 2 on y. I will just use this itself, but I don't have to. Yeah. Let's use a different color. And to be able to see this, let's give a system sleep so that we can see how it is for 5.5 seconds, so that we can see how it is progressing slowly towards one of these optima points. Okay, so I think that's it for the one variable evolutionary strategy. So let's see if this works. So if you see here, the green dots are appearing, and so okay, so I and somewhere this particular place they are going towards the solution. So I think let me give a 1 second pause, and then let's see. So if you can see the green, the solution is moving towards, okay, in this case it is moving towards the right side optima. Yeah, so if you can see, it has gone towards the right side of optima. So is this clear, Mr. Manohar, how this is progressing towards the optima?
Yes, sir. Yes, sir.
Okay. So now let me show you what happens if we have a bigger sigma. So in this particular case, we took sigma of 1. So if you see the difference between the speed with which, or the distance it covered in one iteration, was a little bit bigger distance. So if I reduce it to, let's say, zero point 0.5, and to give it opportunity to reach the optima, let me give the number of generations or iterations as 200. Let's see if we can have a little smaller step. If you see here, the steps are a little bit smaller than previous steps. So that is what the effect of sigma, or the value of sigma, is. If you have smaller sigma, it may take a long time to reach your optimum solution, but it will reach. If you give a sufficient number of like iterations, it is going to reach to your optima solution. But let's say if I give a very big sigma, in this case let's try to give 5, then you will see it is going to haphazardly move here and there, and it may not even converge to your optima point. So now I have given sigma 5. So control enter to run. So let's see. From initial, it directly went to this particular thing, and it is oscillating. Yeah, it didn't converge. If you see this, it didn't even converge to the optima solution. It was just oscillating near the optima. So why it only plotted these many points? Oh, so by accident it has converged. Let me try to show you this thing. Yeah, so this is what I was talking about. It's still learning. Oh no, it's done. So see, some cases it may reach like the previous one, and some cases it may not reach. Why that is? Because, so let's say we have a big sigma. So in this particular step, when we introduce the randomness, it is going to change these particular x1 and x2 by a very huge amount. And when it does, so let's say by some luck, let me zoom it and I'll show you. Let's say by some luck you have reached an optima point, that is this green one, the near the one level 1 contour. Then the next randomness, or the next point that you will get, is going to be dependent on the sigma. So in this case it is 5. It will be either here, it can be in this particular radius. So it is not going to come here, we are very close to the one where the actual optima lies. So this is the best it is going to do. But in some cases what can happen is, let's say from this green it went to here, and from that it came to the actual optima. So that can happen. So in that case you will get a nice solution, but it is very unlikely that it is going to happen. And most of the cases we are not going to get our best solution. So that's why we have to manage how we use the sigma. So is that clear, Mr. Manohar?
Yes, sir. Yes, sir.
Oh,
Taking the lesser value of sigma may increase the time,
yes.
but taking too large value may take you away from the real convergence.
Correct. No, yeah. So it will. There is a very high probability that it is not going to go towards the actual optimum
Actual
solution.
mean,
Yeah.
actual optimum solution.
Yes. Correct. Okay. So we have understood this from the one population size uh, evolutionary strategy. Now let's try to go for a multiple, like n number of population size in this evolutionary strategy. Let me create a new script. Save it as question 2 and save. And let me copy most, because not lot of the things are going to change. Okay, so let's decide on the uh, multi population size initial population. Okay, so here we gave it x1 as 0 and x2 as 0. Now what we want to give a solution where x1 varies within this -5 to 5, and x2 also varies from -5 to 5. So the best way to initialize any population in randomly inside a grid or a bounding box is to use uniformly distributed variables. So again, random variables, uniformly distributed random variables. So as I said, that R has a very nice way to generate normally distributed random variables. Similarly, it has a very nice way to introduce or create randomly or uniformly distributed random variables. So that is R uniform. So like norm of normal distribution, it has the unif of uniform distribution. In this also, you what you give is, you give a number of values you want. Let's say I want 10 values, and uh, what is the lower limit? Let's say I am going from -5 to 5. You will see it has randomly generated -5 to 5 10 number of variables. So we are going to do this to get the initial population. Okay, so let me just copy this itself and paste it here. So let's say if I want x1 to be this and x2 to be this. So if I do this particular operation again, so you will see that both the times I am getting different values. So we can be sure that we have a quite variety of like we don't get the same variables inside this R unit unless until we perform a random seeding, which actually limits the puts a restriction for the random function to give the same value over and over. So we are not going to do that. So we will have different value in x1 and different value in x2. Okay. So now I want to combine this into my initial population. So let's see how we can do that. So since this is a column variable, so let's see if we have to use C bind or uh, R bind. So let's try to use C bind. So it will combine the two columns and into one. C bind. What do you want to bind? X1 and X2. And just to be sure that we are actually getting the same thing, let me just run this. We have run and the initial population is in x naught. So basically what I should get is let me just show you what I am aiming to do here. So here we have x1 as some particular 10 size and x2 10 size. I want to get x naught, which will be x1 and x2, like this. So for that I have used C bind, that is going to bind the columns. So let's see if this is working or we need to perform some kind of we need to perform some iteration or something to get that. So it's up it seems to be working. As you can see, x1 and x2 both are arranged in the columns of this initial population, and we can also plot them. Oh, okay, yeah. So in this case, if you see, what I want to do is I want to plot all the first, the first column of this x naught for x1 and second column of the x naught for x2. So what I will do is I want to select all the rows for this first column. So the way to select this is x naught square bracket comma 1. Then for the second column, x naught square bracket comma 2. So what this when you do this comma before, it will select all the rows for the first column, and when you do this comma, it is select all the rows for the second column. So let's say if I do one comma, then if you can see from here, it is going to select these particular values, so all the columns for the first row. So let's see if we can see. So you can see it has plotted the 10 randomly generated points inside this particular domain. Okay. So is that clear, Mr. Manohar?
Yes, sir.
Okay. So my earphone may die out soon. So you might have to tell me if my voice suddenly stops or something happens. You can tell me. Okay. So now what we have done, we have given our initial population, but initial population size is 10. So 10 sets of x1, 10 sets of x2. Now we have to calculate the value of the function at these particular points. Again, we have to do all the rows for this first column for x1 and all the rows for this second column for x2. So we use the same thing, square bracket comma 1 and square bracket comma 2. Okay. Now we need to do the same thing for the randomness. So one problem that I feel that this particular random generation function has in this R is that it is not going to give you randomly generated variables in a matrix, or maybe it can give, but I'm not aware of that. So what this particular function is going to do is it is going to give you in only columns only. So we can see here I will use R norm, and let's say I want in this particular case I want 10 like 10 cross 2 matrix with this. So we cannot give 10 cross 2, we have to give 20 with 0 mean and standard deviation of sigma, and we get this particular 20 cross 1 kind of array, and we have to reshape it to make into this particular matrix so that we can easily add just like this. So let me show you how do we do that. Previously we had only two two variables, but now for the same two variables we have 10 sets also. So we actually need 10 cross 2 random variables. So 20 in this particular case, so it is going to create randomness with that is 20 cross 1, similar to the above one, and we have to now arrange it so that it takes a shape of a matrix. So we can do that using the array function. So we use array. Inside this we give randomness, and then we give dimension. Dimension we have to specify in an array like m cross n. So to specify an array of two variables we use c, and inside this we are going to give it the number of rows, that is 10, and the number of columns is 2. So 10 and comma 2. So this is going to transform this randomness into a matrix form. See, it has transformed this randomness into a matrix form. Okay, so since I gave sigma of 5, it has given a very large value. So will rectify that. Let's make it 1. So now we have randomness, and we can directly add these two matrices so that we give a mutated value of new generation, that is 5. Now again, can you tell me, Mr. Manohar, is there something wrong in this thing? Do I have to change this to calculate the value of fitness function?
Now we have to consider all 10 combinations, no?
Yes, exactly. So we have to give here comma and comma so that it takes all the rows for this first column and all the rows for
And
this
all
second
the
column
rows
as
in
x1.
second column.
Sorry.
Yes, sir.
Yeah.
Same thing.
Okay. So now that we have f0 and f1, now here is the trick. We can now we have to update our initial solution based on whether we have improved it or not. So I personally, so what sir had done was, if you remember, let me go to the, yeah, let me go to this. So if you remember, what sir had done was, so we had x and we had y, 10 cross 2, 10 cross 2. Then he combined these, so it became 20 cross 2, and then we performed some kind of selection operation. For in this in Sir's video, what he did was he arranged them in increasing order, and then he selected the top 10 and got a new generation, that is 10 cross 2. Is that correct, Mr. Manohar?
Yes, sir.
That is what sir has done. So for to
Yes,
do
sir.
this, yes, Mr. Okay, so to do this, what sir had done was he uh, made this matrix into a data frame, right? And then he combined f here, x2 here, x1 here, and then he sorted this data frame based on the value of f. Do we have a?
No, sir. No. He's. I got that.
Oh, okay.
He sorted the F column, which
Yes.
accordingly other column were getting sorted.
Yes, exactly. And then he did that. But the thing is, I what have faced the difficulty in MATLAB is whenever you try to, introduce a table. Basically, data frame is nothing but a table. So it slows down the speed of the algorithm. So we can do the same thing, but without using the. There are two methods to do this actually. So let me show you what they are. So one is you can actually concatenate these two things, and you can do the sorting. And another method is you can, without concatenation, you can update the value of x at those indices where the new mutated generation is better than the previous generation. So let's see both the cases. How do we do this? Okay, so now we have f1 and f0 to compare. Let me just remove this. So what I want to do is, okay, let me use my use the iPad again to show you what I am actually wanting to do. Where is that? Okay, so I have stopped sharing by mistake. Let me just share again. Okay, so can you see this? Okay, yeah, can you see the screen?
Yes, sir.
Okay, so what I want to do, a much easier approach we can adopt actually. Let's say we have x, we have y. There are, let's say we have 5 entries. Then we have f0 and f1. What I do is I compare the f0 and f1, and I choose the indices where f1 is less than f0, means f1 is better than f0. So let's say this second is indices is where the second and fourth index is where my new generation or mutated generation is better than my previous generation. So what I can do is I can keep this first, third, and fifth value from my old generation and use this second and fourth value from my mutated generation to get a x. That will be x of 1, x on y of y with 2, x with 3, y with 4, and x with 5. So we can do this very easily without having to concatenate it and do the sorting. So that this is one way, but this may cause some problem. Let's see how to do this, and let's see how to do what sir was doing in the class, both the things, without using the data. So you understand what I am trying to do here, right?
Yes, sir. Yes.
Okay.
Understood.
So let's see how we can do that. What we can do is we can use the logical operation that is there in the uh, R. So f indexes where f1 is less than f0. So let me see if we can run this. Let's just run this one more time, and run this one time. So we have calculated f0 and f1, and let's see what we get when we calculate this. Okay, so if I just type index here, what do you think the output will be, Mr. Manohar? It will be in which form? So there was one question also in last week's assignment. So it will be in the Boolean form. So what this tells me is, for first case, like for the first index, your f1 is less than f0, so it is true. For second, that is, this particular thing is not true. For third, fourth, fifth, this is true. Fifth, it is not true. Sixth, seventh, it is true, and then so on. So do you understand, Mr. Manohar?
Yes, sir. Yes.
So what I can do is I can take my x0, and I can just use this. So this is the index of for the rows, and corresponding to these rows I have to change both the columns for this x naught by y. So I give comma here, which is going to say to my x naught that for these indices where it is true, change both the columns of these x naught by the y, by the entries in the y. So if we can just move this back. So is this clear? Now I have my new updated X now. Then again it is going to go to this calculate, introduce randomness and update, and again it is going to go, and it will go do this for, let's say, 100 activities. So is there any doubt, Mr. Manohar?
No, sir.
So let's try to see what we get, or if there is any error that I have introduced. So again for plotting, I am selecting all the rows for this corresponding column. So Control S, Control A, and if you see here, we have our X naught, and it is slowly converging towards the good solution. So I think it is keeping the old green dots also. So what I will do is, I will stop this, I will clear this, and I will plot this outside this 2, so that we only see the solution in the end. So Control A, Control Enter to run this. So if you see here, we see all the 4 optimas have been covered by this particular method. So is this clear, Mr. Manohar? I will run this once more. Again, all the 4. Final, I am showing only the final because for some reason it was not erasing the old dots. So we can actually do that. Okay. So Control Z. We can actually do that also by plotting the contour one more time. But I have changed here x1 and x2. So let me see how we can do this. It will be much more clear when we are doing this. So let me give here x x1 and x2, x1, x2. So I think now we will see that the old green dots would have been cleared by the new. So let's see if this works. So then now you see the old will be erased, and you can actually see how the solution is converging towards each of the optimum points. So slowly, if you see, they are converging towards the optimum solution. I have given pause for 1 second, so that's why it may take some time. But anyhow, it is for better visualization. So let's wait a while and see it converge towards our all the optimum points. So how do we know that the program is still running? Is using this particular, seeing this particular red button here. When this up disappears, that means your program has stopped running.
Okay, another thing that we can get arrow in the console at the end.
When
There.
here, yes, miss, we will get error, but if we our code doesn't have, oh, arrow, yeah, we can get arrow, yeah, that is true, that is true. I thought you meant error, so I was confused. So yeah, you see, slowly, all our solutions have converged towards the available optima points. So it's taking too much time, but I think we understand this, so I will stop this here. Yeah, okay. And let me just plot it so that we have something to see. Yeah. So slowly it would have converged more towards the optimum. So this is one way. So Mr. Manohar, will it be fine if we go a little bit over time, or do you want me to finish on 5 o'clock
It
itself?
is okay, sir. It is okay. We can extend. No
Okay.
problem.
Okay. Yeah, so I will upload this video in two part actually, so that it doesn't take that much time to upload into YouTube. Yeah, so this is one of the ways to perform this big population size uh, evolutionary strategy. There is one more way which is more common or more similar to what Sir had done, the sorting. Let's do that. So I'm going to create a new script. So I'll save it as E and sorry, control A, control C, and control V. All these things are same. Only few things are going to change. That is, we are going to use F1 and F0 to create a new F, and we are going to sort those, and we are going to use that particular sorting to actually sort the X naught and Y. So let's see how do we do this. Let me just erase this here and erase this here and perform. Let me perform these again and uh, perform our calculation for mutation function. Okay, now we have Y, we have X. Oh, we have X naught. Yeah. Let let us create a new like Sir did. Let us create a new matrix with which is called X, and that matrix has these X naught and Y arranged one top of the other, like in case of uh, in Sir's case, like concatenation. So for that we have to do row bind. Sorry. And what we want to row bind? We want to row bind X naught and Y. Let's see how does this look like. So if you see, we have 10 cross 2 X naught and 10 cross 2 Y naught. Now we have 20 cross 2 X naught and Y naught on top of the other. Same thing we are going to do for F also. So let's name this F12 and do our bind for F. Okay, so I don't. Is my voice still audible?
Yes, sir. It's audible.
Okay, I think it's about to die now, so I will remove my earphones so that. Okay. Now is it audible, Mr. Manohar? Hello. I am not able to hear. Mr. Manohar, my voice is audible now. Okay, it doesn't seem to be. Let me reconnect it. Hello. Can you hear me, Mr. Manohar? Hello. Let me check my internet connection. If you can hear me, then Mr. Manohar, can you type if you can hear me? Okay, so there seems to be some kind of problem. Hello? Settings, internal mic. Uh, Mr. Manohar, can you hear me?
Yes, sir.
Oh,
Yes, sir.
thank you. Sorry about this. My earphone actually died finally. So if I am audible, then let's continue this. So what we have done till now is we have obtained our x naught, our new x by concatenating x naught and y, and same thing we are going to do for the values also. So f naught and f1. So let's see. So here's a, it is always good to check what we are actually getting after concatenation. Why? We will see now. See, f value, what we yes, Mr. Manu.
No, sir. No.
Oh,
You can continue.
okay. So what we actually see here is that we did the row bound, but our the values of this particular function is not what we expected. We expected it to be 20 cross 1, but it has come to us as 2 cross 10. So let's see if the C bind can fix this. Okay, so we have done C bind. Let's run this. So when we do C bound, we get this as 10 cross 2, and so this is still not what we want. So again, what we are going to do is we are going to use the function, uh, reshape this function to our liking. So we have f naught and f1. So that is stored in this thing. Let's put it here and give the dimension. Dimension is what we want, 20 cross 1. So let's see if we are so after this also we are going to check what we have. So what we should have is f1, sorry, f naught, and then f1. So in doing this reshaping using this array function, we can sometimes it can sometimes give wrong value also. So we will check wrong order also. It can we want 52, 4, 45, and then after those things, after 275 we need 336. So let's see if this is giving us that. So if you see, it is giving us the correct order, so we are going to use this. Is this clear, Mr. Manohar, why we have done this?
Yes. Yes, sir. Yes.
Okay, now we are going to use the indices that are that give us the increasing order of the functions in this fval. So let me give the variable index and use a function called order and put fval inside. So one nice thing about this function is, let me show you by creating a uniformly distributed random variable, 5 random variables between -1 to 5. So we have these variables, and let me save them also, so that we have some correct -1 to 5 here. So we have these variables inside A. Now what I want to do is I want to know, I want to arrange them in increasing order. So I will use this order, or we can use the sort function. So it is going to arrange this in increasing order. But this is not what we want. We want the index of this thing, right? So what is the index of this 1.625 here? It is 5 in this particular case. So if I somehow know the indices of the functions in increasing order, indices of the values, so that I can put them inside the function and get the increasing order, it will be very nice. So for that we use the order function. So let me show you what this order function does. So let's say I do the order of A. It is going to give me 15432. And when you put these indexes, when you look at these indices inside A, that is this one, what you will see is A of 1 is 0.536, A of 5 is 1.625, A of 4 is 1.812. So you see that if you put these indices inside A, you are going to get A changed into the increasing order. So let's do that. Let's see whether what we are saying is correct or not. So if you put these indices inside A, you should get the same thing that you get by using sort of A. So let's do that. So what we see is we get exactly the same thing that we are getting by sorting them. So we can use this function to arrange these things, arrange the functions in increasing order, and same indices we can use in our x also to get the top 10 or n number of solutions for our new generation. So is that clear, Mr. Manohar?
Yes, sir. Yes, sir.
Yeah. So we have indices. So it will have 20 elements. We are going to select first 10. Let's say if I want to select first three, the smallest three, I will select 154 here. So it will be order from 1 to 3. So I'm going to use that. So let's say my new x naught is now x, and indices are going to vary from 1 to 10, and I need all the columns, so I will give comma here. I don't need this particular thing. This was for previous thing, so I don't need this. So I will put a comment here. Get the index of increasing order and select the top or the smallest 10 values. So this is our new generation now. So is this clear, Mr. Manohar?
Yes, sir.
Okay, so now let's plot it and let's see. I will give a small pause here so that we don't spend too much time on this. Oh, so it seems that we have some kind of problem. Let's see what we have. Okay, so since we introduced a new variable with the same name as fval, so it is asking us that you have changed the fval from the grid value to something else, so we cannot plot the contour. So to avoid that, let me just give it the value of fval1. Save it, select all, control enter. Now it should work. So now we will see the solutions are much faster, converging towards one or maybe two optimal solutions. So let's see what we get in the end. I hope we should get some good solution. One of at least one of the optimal points. Okay, so it seems that we have done some kind of mistake. Is that so? So maybe like last time again I have done some kind of mistake. Do you see any mistake here, Mr. Manohar? That's a good thing about programming. We can do the same thing again and we will find some kind of mistake. It seems to be working fine. X naught is index of X population size from 1 to 10, because that's how many we wanted, and we selected all the X's for that. Let me see if my sigma is too big or too small. And let's just not spend too much time on generating this. Comment these things and not the final thing. Let's see. It seems there is some kind of an issue. FL1, FLC. Oh, okay. So if you see here, Mr. Manohar, I have put this FL, but I have done a mistake by not putting here FL1. So it is rearranging my this grid in this particular array function into getting a new FL, which is completely wrong. Which is completely wrong. So let's see. So if you see, now we have obtained some one optima point. So I can run it again, and we have obtained two optima points. If I run it again, we have obtained some different optima points. So I hope this is clear. This approach. See, again we did some mistake and we found out. Luckily, a little sooner than last time. So is this evolutionary strategy clear, Mr. Manohar?
Yes, sir. Yeah.